Hi, today we will work on a review of matrices. The very basic concept here is the concept of a matrix, which is basically a concept that will allow us to group numbers and to be able to work with all the numbers at the same time. So we want to manipulate all those numbers. Um, a typical way of representing those numbers is, or grouping those numbers, is that we have a big parenthesis and then maybe have the array of numbers like 5, -1, 2, and 6, 0, and 9. So in this case I have 1, 2, 3, 4, 5, 6 numbers, which in this case are all integers, and then I'm grouping those and using that structure, and then I say that this is my matrix A. Now with this range of numbers I also have associated a size, so the size of matrix A is 2 by 3. The 2 represents the number of rows and the 3 represent the number of columns in the matrix. So if I have another matrix, let's say I have a matrix B, and then this is 0, -1, 7, and 2, then the size of this matrix is a 2 by 2. Okay, so you see this is basically very similar to the concept of an array in programming languages. And now something that we want to do with those numbers, maybe to manipulate those, is that there are some basic rules like, okay, if we want to do the addition or subtraction of the numbers, the matrices, what we need to do is having two matrices of the same size. Like for example, if I want to do A plus B that I have on top, so this is not allowed, so we say no, this doesn't exist. So I could maybe define another matrix which is C, and let's say that this is the same size as B, and this is 3, 7, 9, and 3. So now I could do B plus C, which in this case it will be 3 plus 0, which is a 3, 7 plus -1, which is a 6, 7 and 9. So you see I'm adding the correspondings. So this is 16, and then 3 and 2, this is 5. Subtraction works the same way. If I do B minus C, then I will be subtracting the corresponding, like in this case I will be doing Z minus 3, -1, minus 6. Now if I want to do C minus B, it's not the same as B minus C. Oops, so you don't see that. And however, B plus C, it will give us the same answer as C plus B. Okay, I think you can see those concepts. Now we also have the scalar multiplication. So in this case is the multiplication of a number and a matrix. For example, let's say that I want to do 7 times matrix A, which is the one that we have here. So what this is doing is multiplying all elements inside A. This is like the distributive property, so it's doing all the numbers, the inside A, which is 7 times 5, so that will give me 35, and then this will be -7, 14, and 42, 0, and 63. Now something else that I didn't mention is that in matrices we also refer to a position. So in this case, this is in the position 1 1, and so that means there is an index associated, which is first row and first column. So then the 0 will be on the second column, on the second row, second column. Now, okay, um, so again, the size for 60, the size, I'm sorry, the location of 63 in the matrix will be second row, third column. So that's the position 2, 3. What I want you to notice too is that this might be different from most programming languages, because usually if you remember the indexes in programming languages start with 0, 0, right? So usually the first element here it will be addressed as 0, 0, and they call the first column column 0, and then this will be column 1. Notice that I'm calling this row, I'm sorry, row 0 and row 1. Look at that, I'm calling that 1 and 2, so it's just um, some little disagreement there, the way the word is the first element. So we just need to be careful that if the 1 1 in our notation is the first element here, or mean that the 0 0, once we're going to be working in actually programming this, and we're going to be doing that very soon in the other tutorials. Something else that I want to give a brief review that I'm hoping that maybe most of you saw someplace else, matrices, is the product of two matrices. So if you remember, I just say that for subtraction and addition, the condition is that matrices has to be the same size. In this case, for two matrices to be able to have the multiplication, the let's say, yes, as an example, this is matrix A, and matrix A was of size 2 by 3. So the columns on the first matrix, they need to be the same as the column on the second matrix. So let's say that we have a D matrix, and the D matrix is size 3 by, so these two numbers needs to match. So then the number of columns on the first one, they need to match the number of rows on the second one, and the resulting matrix will have size of the number of rows here and the number of columns here. So you have here a 1, the resulting matrix will be a size 2 by 1. So let's say for the time that this is size 2, so the resulting matrix will have size 2 by 2. So let's have a quick example. So let's copy matrix A again. So matrix A was 5, negative 1, 2, 6, 0, 9. And let's now have a matrix D that has to be 3 by 2. So I will make these 1, 2, and 1, 0, negative 3, and 0. So this is 3 by 2, this is 2 by 3, then it's possible the multiplication. So if we don't have this, the number of columns in the first matrix is not the same as the number of rows on the second one, then the multiplication is not possible. And the way that this works is, so here we got a row and column. So what we do to get the first element, we get the whole row, which is this, with the elements on this column. So we say, okay, let's call the answer matrix M. So let's say now that M, the first element is going to be row 1, we multiply by this column. So this is 5 times 1. So we do 5 times 1 plus negative 1 times 2. So I'm doing now this, and then plus 2 times 1. And then for the next element, which is going to be the 1 2, that means row 1 with second column is going to be, it's going to make this a little faster, so this is 0. Negative 1 times negative 3, that's a 3, and a 0, so the answer for this is 3. And the answer for here, let me put it here, so this is 5. Oops, here, should be a plus. So let me repeat the first one because I got here a time. So it's 5 times 1. So 5 times 1 plus negative 1 times 2. Negative 1 times 2. Then plus 2 times 1. Okay, so this will give me a 5. So this is 5, negative 2 plus 3 and 2. So this answers to 5. Okay. Now let's do the same. 6 times 1 is the next row with the column. 6 times 1 is the 6 plus 0. 9 times 1 that's a 9 and a 6, so this will give us a 15. And the next one, this is 6 times 0 is 0, 0, so that was an easy one. So matrix M is 5, 3, 15, and 0. And here I was trying to do all the steps, illustrating that the first element from here multiplies that element. The first element of this row multiplies the first element of this column, and then we follow that sequence. So this multiplies this multiplies this, and then we're adding them. So here I think I say it and I put a times. Okay, something else that we want to review here is the concept of determinant of a matrix. So this it is a value derived from a 2 by 2 matrix. For example, the determinant of this matrix is 5, 6, 7, and 9. So this is what we do. It's 5 times 9. So what we do with this multiplication, so it's 5 times 9 minus this multiplication, 7 times 6. 7 times 6. So this is 45 minus 42. So the number associated with that 2 by 2 matrix is 3. Let's just have one more example. Let's say that we want to find the determinant of matrix 1, 7, negative 3, 2. So like we say is we multiply these two numbers, 1 times 2, 1 times 2 minus the multiplication of these two numbers. So this is negative 3 times 7. So this will give me 2. This is negative 21. With that minus becomes plus 21. So this is 23. Now, what about other matrices from other sizes? Well, we can only compute the determinant of a square matrix. A square matrix is the one that has the same number of columns. So columns equals rows. So that's a square matrix. Now, what about when it's a 3 by 3? What about when it's a 4 by 4? In the definition, it says that is the number associated with a 2 by 2. So this is how we do it. I just want to have the illustration, and I will make a reference in the in D12 for you to read more of these exercises. So for example, if we want to compute the determinant of a matrix that is 3 by 3, so 5, 6, 7, negative 1, 2, 3, 6, 7, and 9, this is how we do. So we associate this number, and then we do an imaginary elimination of row and column that are in that position, and this will give us the following: 5, and then the determinant also we do with our bars. So this is, and then here we got a 2 by 2, 2, 3, 7, and 9. So we compute the determinant of this times 5, and then from this we also follow some rules with the signs. So we say this is this, we don't change the sign, so which means it's a plus, there is a minus, there is a plus. The plus says we keep whatever sign they have it, the minus means we change the sign. So we can go any row or any column to compute the determinant. So I can pick this one, or I can do this column, I can do this row, anyone. So usually, because we got the flexibility, we try to pick the one that has the most zeros, because that will eliminate and simplify the computations. So following this rule, the next one will be 6, and then we change the sign, 6, and then we compute the determinant or whatever at the numbers. I mean, we will eliminate that column and that row. Then we got another 2 by 2, that is -1, 6, 3, and 9, and then finally plus 7, which is -1, 2, 6, and 7. So if we want to compute this will be 5 times 2 times 9, 18, minus 21, and then minus 6, -9, minus 18, plus 7, times -7 minus 12, and we just simplify, and this is -3, -15, so this is 27. Okay, to save some time I paused it and I was doing those computations. So I mean -9 minus 18 times -6, and then the same, so I got the final answer to 80. So we'll make a reference to other information about this in the content area of D12, and so this will be the end of this tutorial.